For the first time in recorded science, researchers have watched a tectonic plate come apart in real time, not in a simulation, not in a lab model. In actual images of the seafloor, gathered off the coast of Vancouver Island, showing a slab of solid ocean crust ripping into pieces as it sinks into the earth. The plate in question is the Juan de Fuca Plate, the same slab of oceanic crust that feeds directly into the Cascadia Subduction Zone, the fault system that sits offshore from Seattle, Portland, and Vancouver, and the fault capable of producing a magnitude 9.0 earthquake. So when scientists say this plate is behaving in a way nobody has ever documented before, that's worth slowing down for. This piece walks through exactly what was found, how it was found, what the leading researchers actually said about it, and, just as importantly, what it does not mean for anyone living along that coastline. No exaggeration required. The real science is strange enough on its own. Before getting into the mechanics of the discovery, it's worth sitting with why this particular region draws so much scientific attention in the first place. Cascadia isn't just another fault line on a long list of the world's subduction zones. It's one of the few subduction zones on Earth that sits directly beneath a heavily populated, highly developed coastline, and it's one that has already demonstrated it's capable of producing a rupture on the scale of the largest earthquakes ever recorded. That combination, genuine catastrophic potential paired with a dense population living almost directly above it, is part of why any new finding about this specific fault system tends to travel fast, and why it's worth being careful about separating what was actually found from what gets added on top of it in the retelling. A 5-year-old survey, a brand new discovery. The story starts back in 2021, when a research vessel called the Marcus G. Langseth, operated by Columbia University's Lamont Doherty Earth Observatory, sailed the waters off Vancouver Island. Its mission belonged to a project called CASI-21, the Cascadia Seismic Imaging Experiment of 2021. The technique researchers used is called seismic reflection imaging. In simple terms, it works like an ultrasound for the planet. The ship fires powerful pulses of sound down through the water and into the seafloor. Those sound waves travel through different layers of rock, bounce back at different speeds depending on what they hit, and get picked up by instruments trailing behind the vessel. Piece enough of those echoes together, and you get a cross-sectional picture of what's happening thousands of feet below, structures that are otherwise completely invisible. It took years to process and analyze that data. Seismic surveys like this one don't produce a finished picture the moment the ship returns to port. The raw signal has to be cleaned, filtered, and reconstructed into a coherent cross-section of the crust, a process that can take a research team years of careful, iterative work before the underlying structure becomes clear enough to publish. The results were finally published in 2025 and 2026 in the journal Science Advances, led by geologist Brandon Shuck of Louisiana State University, working alongside Suzanne Carbot of Lamont Doherty and other collaborators. What they found surprised even the people who'd spent years looking for it. It's worth understanding just how much technical effort sits behind a single image like this. The Marcus G. Langseth doesn't just fire sound waves downward once and read the result. It tows long streamers of hydrophones behind the vessel, sometimes for miles, recording the returning echoes from dozens of separate sound pulses as the ship moves along a survey line. Each of those recordings captures a slightly different angle on the same underlying rock structure. Stacking and processing thousands of these recordings together is what eventually produces a sharp, continuous image of the crust, rather than a blurry, ambiguous smear. That's part of why this kind of survey is expensive, time-consuming, and relatively rare, and part of why it took until years after the original 2021 expedition for a picture this detailed to emerge. The DERS, not sinking whole, tearing apart. Here's the core discovery. The Juan de Fuca Plate, along with a smaller neighboring slab called the Explorer Plate, is not descending into the mantle as one continuous, unbroken sheet of rock. It's fragmenting, splitting into distinct pieces as it goes down, some sections still actively sliding beneath North America, while others have essentially stalled or detached. Along one major fault, researchers are calling it part of the Nootka Fault Zone. The imaging revealed a vertical drop of roughly 5 kilometers, 3 miles of solid oceanic crust, offset downward in a single structural break. To put that scale in perspective, that's deeper than Mount Everest is tall, in a slab of rock large enough to influence an entire regional fault system. Shuck summarized the finding about as plainly as a geologist can. This is a subduction zone caught in the act of dying, and it isn't dying all at once. It's dying piece by piece. Carbot, whose earlier work laid much of the groundwork for how researchers currently model subduction zone behavior in this region, described it in similar terms, noting that this is the clearest picture scientists have ever had of this exact process happening in real geologic time, rather than reconstructed after the fact from cold, ancient rock. That distinction between inferred from old Evidence, and observed directly while it's happening, is a meaningful one in geology, where most processes unfold far too slowly for any single research career to watch from start to finish. Catching a subduction zone in the middle of its own breakup, with modern instruments precise enough to actually resolve the structure, is closer to a once-in-a-generation opportunity than a routine finding. That distinction matters more than it might sound. Geologists have understood the broad concept of subduction zones shutting down for decades. Buoyant material reaching a trench, changes in plate motion, shifts in mantle flow. There are several theoretical mechanisms that can stall a subducting slab over geologic time. What nobody had was direct, high-resolution proof of the mechanism actually happening, captured in progress rather than reconstructed after the fact from ancient cold rock. This is the first time that process has been imaged this clearly while it's still underway. Sorry. What subduction actually means? In plain terms, it's easy to lose the thread of a story like this in technical vocabulary, so it's worth pausing to define the basics clearly. The Earth's outer shell is broken into large plates of solid rock that float, very slowly, on a hotter, more pliable layer of mantle underneath. Where two plates meet, several things can happen depending on their relative density and direction of motion. Sometimes they slide past each other sideways. Sometimes they pull apart, letting new crust well up between them. And sometimes, when one plate is denser than the other, usually because it's made of heavier oceanic rock rather than lighter continental rock, it gets forced underneath its neighbor and sinks down into the mantle. That process is subduction, and the boundary where it happens is a subduction zone. Subduction zones are responsible for some of the most dramatic geology on the planet. As the descending plate sinks, it drags water and other material down with it, which lowers the melting point of the surrounding rock and helps generate the magma that feeds volcanic arcs. Chains of volcanoes like the ones running through the Cascade Range, including Mount Rainier, Mount St. Helens, and Mount Hood, all products of the same subduction system now being studied off Vancouver Island. At the same time, the interface between the two plates can lock together under enormous pressure, storing up strain energy for decades or centuries before, releasing it all at once in an earthquake. The largest earthquakes ever recorded, the 1960 Chile earthquake, the 2004 Indian Ocean earthquake, the 2011 Tohoku earthquake in Japan, all happened on subduction zone megathrusts, and Cascadia is built on exactly the same kind of fault. What was never well understood is what happens at the end of a subduction zone's life. What physically occurs as the system runs out of plate to consume, slows down, and eventually stops. That's the gap this new research is starting to fill. Deryange, why Vancouver Island, specifically? The northern end of the Cascadia Subduction Zone is geologically unusual. It's where three separate tectonic plates, the Juan de Fuca, the Explorer, and the Pacific, meet near the North American plate in a tangle of ridges, transform faults, and trenches. The Explorer plate, in particular, is small and has been slowing down for millions of years compared to its neighbor. That slowdown is visible in modern GPS data. Instruments tracking the Explorer plate's motion relative to North America show it converging at roughly 2 centimeters a year, less than half the rate of the Juan de Fuca plate just to the south, which is still pushing forward at closer to 4 centimeters annually. As the Explorer plate's pull weakens, researchers believe the gravitational force that once dragged it downward is being partially transferred onto the Juan de Fuca plate instead, adding stress to that side of the system. You can even see this asymmetry in the shape of the seafloor itself. The deformation front, the ridge where the incoming plate first starts bending downward into the trench, bulges outward on the Juan de Fuca side, where the plate is still pulling hard, and pulls back landward on the Explorer side, where that pulling force has largely given out. It's a visible physical signature of one plate still working and another plate quitting. Put those pieces together, and you get a natural laboratory, a subduction zone that is shutting down unevenly at different speeds in different places, all within a relatively small and heavily studied stretch of coastline. That's exactly the kind of setting that lets scientists watch a process in motion instead of only inferring it from old, undated rock. The Nootka Fault Zone itself plays a central role in this story. It's a transform fault, a boundary where two plates slide past each other horizontally rather than colliding head-on, that runs roughly perpendicular to the main subduction trench, cutting across the boundary between the Juan de Fuca and Explorer plates. Researchers found that this fault appears to be doing double duty, not only accommodating the sideways motion between the two plates at the surface, but also extending down into the subducting slab itself, effectively slicing the incoming oceanic crust into separate blocks before or as it descends. That's a structurally unusual role for a transform fault to play, and it's part of why the imaging results were considered such a significant methodological advance. Instead of one clean, continuous subduction interface, researchers found a segmented patchwork, with the transform fault acting almost like a perforation line running through the plate. The result reads almost like a maintenance record for a machine that's slowly failing in sections rather than all at once. The Explorer segment losing momentum first, the Juan de Fuca segment still under load, and the Nootka fault zone acting as the structural boundary where the difference in behavior between those two sections is being physically expressed as a tear. Prachmaras, rewriting an older mystery. This discovery doesn't just explain what's happening today off Vancouver Island. Researchers think it may finally explain something that's puzzled geologists for years, thousands of miles away. Off the coast of Baja California, scientists have long identified strange chunks of ancient oceanic crust that don't match any subduction system currently active in the region. Geologists call these fossil microplates, leftover fragments of the old Farallon plate, a massive tectonic plate that spent tens of millions of years sliding beneath North America before it eventually vanished from the geologic record. For decades, researchers understood these fragments as evidence that a subduction zone in that region had shut down at some point in the deep past. What they didn't have was a clear picture of the actual mechanism that produced fragments like that in the first place. The tearing now being observed off Vancouver Island looks like a live version of exactly that process. If a subducting plate breaks into distinct, disconnected pieces rather than shutting down as a single unit, that would naturally leave behind a scattered field of fragments, precisely the kind of pattern found near Baja California. In other words, researchers may be watching, in real time, essentially the same process that shaped a completely different stretch of coastline millions of years ago. That's part of why this study has generated so much attention across the geoscience community. A localized finding off one Canadian island might end up reshaping how scientists interpret subduction zone endings everywhere, including systems like Japan's Nankai Trough, Chile's coastline, and the Sumatra Fault System, all of which have their own histories of catastrophic earthquakes and are now being re-examined with this mechanism in mind. The ghost forests and the orphan tsunami. To understand why researchers care so much about getting Cascadia's structure right, it helps to look at the physical evidence left behind by the last time this fault ruptured. Along the Washington and Oregon coastline, there are stretches of dead cedar forest still standing today, more than 3 centuries after they died, bleached, bare trunks rising out of tidal marshland where a healthy forest has no business growing. These are known as ghost forests, and their cause was a mystery for a long time. The explanation, once scientists pieced it together, was that a massive earthquake along the Cascadia megathrust caused the coastal land to drop, suddenly by several feet, letting salt water flood in and kill the trees where they stood almost instantly. The trees themselves, still rooted in place, became a kind of frozen timestamp. And because trees lay down one growth ring per year, researchers were able to count backward from the outermost ring to pin down almost exactly when that die-off happened. That date lines up with something recorded on the opposite side of the Pacific. Japanese written records from around the same period describe a large, damaging tsunami that struck the coast with no local earthquake felt beforehand, an event Japanese chroniclers had no way to explain from their own side of the ocean, since nothing shook the ground. Where they were standing, modern researchers eventually connected the two. A massive earthquake off the coast of North America, large enough to send a tsunami all the way across the Pacific Ocean, striking Japan roughly 10 hours later with no warning at all. Historians now refer to that Japanese record as an orphan tsunami, a wave, separated from its true cause by an entire ocean. By combining the tree ring dating from the Pacific Northwest with the timing recorded in Japan, scientists narrowed the date of the last full Cascadia rupture down to a specific night in January of 1700. That combination of evidence, dead forests on one coast, an unexplained wave recorded on another, is part of what makes Cascadia's risk profile so well established, independent of any new plate-tearing research. It's also a reminder of just how enormous these events can be. A rupture large enough to be felt across an entire ocean isn't a hypothetical worst-case scenario for this fault. It's already happened at least once within the window of recorded human history. What this means for earthquake risk, and what it doesn't, this is the part that deserves the most care because it's also the part most likely to get exaggerated. The Cascadia Subduction Zone is real, and its risk is well established independent of this study. The last full margin rupture happened in January 1700, producing an estimated magnitude 9 earthquake and a tsunami large enough to cross the Pacific Ocean and strike Japan, where it arrived with no local earthquake felt at all. Japanese records from that era describe an unexplained orphan tsunami, a wave with no obvious local cause. It took modern researchers centuries to connect that historical Japanese record back to a massive undocumented earthquake on the other side of the Pacific, using tree ring records from drowned ghost forests along the Washington and Oregon coast to help pin down the timing. Canada's Geological Survey estimates that major ruptures along Cascadia recur roughly every 300 to 800 years, based on geologic evidence in the sediment record. None of that background changes because of this new study. And critically, the research team behind this discovery has been explicit on this point. The tearing they observed does not significantly change the near-term hazard outlook for Cascadia. This isn't a new warning. It isn't a sign that a major earthquake is imminent. It isn't evidence that the region has become more dangerous than it was last year. What it is, according to the researchers, is a piece of missing structural information that could eventually improve how earthquake forecasting models are built. The fragmentation they found is happening on faults separate from the main locked megathrust interface, a specific boundary where stress actually builds up and eventually releases in the region's largest earthquakes. But if the incoming plate is already broken into distinct segments before it fully subducts, that structure could influence how stress is distributed along the fault above it, and potentially how future ruptures propagate. Whether a future Cascadia earthquake tends to break as one long, continuous rupture or as several smaller, segmented ones, that distinction actually matters quite a bit for emergency planning. A single unified rupture along the entire margin behaves differently than a series of smaller, staggered ruptures, different shaking patterns, different tsunami characteristics, different timing. Researchers plan to feed this new structural data into existing hazard models to see whether it changes those predictions. That work is ongoing, and the honest answer right now is that nobody knows yet exactly how much it will change. It's worth being direct about a distinction that's easy to blur in casual retelling of this story. The tier researchers imaged is not the same fault surface that generates Cascadia's largest earthquakes. The megathrust, the shallow, gently dipping boundary where the Juan de Fuca Plate first slides beneath North America, is where stress locks and releases in the region's biggest ruptures, the tearing. Described in this study is happening deeper and further out within the subducting slab itself, well after it has already passed beneath the main locked zone. These are related structures, part of the same overall system, but they are not identical, and finding a tear in one does not automatically mean anything mechanical has changed in the other. The connection researchers are chasing is more indirect, whether the history of how the plate broke apart as it descended left behind structural scars, old weaknesses, or segment boundaries that might now influence how far a future rupture on the shallow megathrust travels before it stops. Why the piece-by-piece framing matters. There's a reason the researchers keep returning to that phrase. Dying piece by piece, not collapsing all at once. It reflects something genuinely new about how scientists understand these systems. The older, simpler picture of a subduction zone shutting down treated it almost like a single mechanical process failing. A plate gradually loses its pull, stops moving, and the whole system quietly grinds to a halt as one unit. What the Cascadia imaging shows instead is more like a structural failure spreading unevenly through a large, brittle object. Cracks opening in some places, while other sections remain intact and still moving, the way a damaged glacier calves off separate icebergs rather than melting uniformly from one edge. That kind of segmented, fragmented ending turns out to match the messy, scattered fragment evidence geologists have found elsewhere far better than the older, quiet, uniform slowdown model ever did. It's a more complicated picture, but a more complicated picture that fits the physical evidence better, which is generally how good science moves forward. A clean, simple story gets replaced by a messier one that actually holds up under closer inspection. Acquire, segmentation, an old puzzle. Getting a new answer, one detail researchers have puzzled over for years, is that Cascadia doesn't behave like a single uniform fault along its entire length. Different sections seem to lock, creep, and slip in noticeably different ways. Southern Oregon and Northern California, for instance, show different patterns of small, slow-slip earthquakes. Barely perceptible tremors that release stress gradually, compared to sections further north near Vancouver Island. For a long time, the reasons behind that segmentation weren't fully clear. Was it differences in sediment on the seafloor, variations in the angle of the subducting plate, something about the composition of the overlying crust? This new imaging offers a more direct physical answer, at least for the northern portion of the system. If the incoming oceanic plate is already broken into distinct blocks before it slides underneath North America, that pre-existing structure could be a meaningful part of the explanation. A fault riding on top of a segmented, fractured plate has a very different mechanical setup than a fault riding on top of one continuous, undamaged slab. Stress could concentrate differently at the boundaries between segments. Ruptures might be more likely to start or stop at those same boundaries. None of that is confirmed yet. It's a hypothesis researchers are now in a position to actually test, using the segment boundaries mapped in this new imaging as a starting point, rather than guessing at their location indirectly through surface measurements alone. If that hypothesis holds up under further study, it would mark a genuine shift in how Cascadia's earthquake forecasting models are built, moving from models that treat the fault largely as a smooth, continuous surface toward models that explicitly account for a segmented, fractured plate feeding into it from below. comparing Cascadia to other subduction zones. Cascadia isn't the only actively studied subduction zone in the world. And part of why this discovery has traveled so far within the scientific community is that researchers immediately started asking whether the same fragmentation process might be happening elsewhere. Japan's Nankai Trough, off the southern coast of Honshu, is one of the most closely monitored subduction zones on the planet, given its history of producing major earthquakes roughly every 100 to 200 years, and its proximity to some of the most densely populated coastline in the world. Chile sits above one of the most seismically active subduction zones anywhere, having produced the largest earthquake ever instrumentally recorded, the magnitude 9.5 event in 1960. Indonesia's Sumatra fault system produced the devastating 2004 Indian Ocean earthquake and tsunami. Each of these systems has its own detailed monitoring network, and researchers studying all three are now revisiting their own seismic imaging data, with this new segmentation model in mind, checking whether similar tearing structures might have simply gone unnoticed until someone knew specifically what pattern to look for. That's often how discoveries like this ripple outward in earth science. A new, well-resolved example doesn't just add one data point. It gives researchers elsewhere a template, a specific structural signature to search for in data they may have already collected but hadn't yet interpreted this way. It's entirely possible that evidence of similar fragmentation already exists in archived seismic surveys from other subduction zones around the world, simply waiting for someone to look at it with fresh eyes. What comes next? This is not a closed case. Researchers plan to return to the same stretch of seafloor for additional imaging surveys, refining the picture of exactly where the plate has torn, how far those tears extend, and how they connect to the rest of the subduction system. Each new survey adds resolution to a structure that, until recently, looked like a single uninterrupted slab. Scientists are also working to determine the timeline of the fragmentation itself. Some of these tears may have developed slowly, over many centuries or longer. Others might form in comparatively rapid bursts. That timeline matters for understanding whether the process is essentially a fixed, ancient feature of this particular plate, or something that's continuing to actively evolve. And if it's still evolving, how that might interact with the stress currently building on the locked portion of the megathrust above it. There's also a broader research question taking shape. If plate fragmentation like this exists off Vancouver Island, is something similar happening at other subduction zones around the world that simply haven't been imaged with this level of detail yet? Cascadia has now become a kind of natural test case, a subduction zone dying in a well-studied, heavily instrumented location, giving scientists a rare opportunity to study the ending of one of these systems instead of only its middle or its beginning. What this actually means. If you live on the Pacific Northwest coast, if you live in Washington, Oregon, or British Columbia, this discovery doesn't change your practical situation. It doesn't lower the risk, and despite how dramatic some headlines have made it sound, it doesn't raise it either, at least not based on anything researchers have confirmed so far. The guidance that applied before this study was published is exactly the same guidance that applies now. Know your nearest tsunami evacuation route. Most coastal jurisdictions post these publicly, and they typically take only a few minutes to look up. Keep a basic emergency kit on hand with water, non-perishable food, and any medication you'd need for several days without power or supply access. None of that changes based on new seismic images of a fault system offshore. Preparedness for an earthquake that could strike at any point in the coming decades has never depended on knowing an exact date. It depends on being ready, regardless of timing. A few common questions answered directly. Does this mean an earthquake is coming soon? No. The researchers behind this study were explicit that their findings do not change the near-term hazard outlook for Cascadia. This is new structural information about the plate's history and internal shape, not a forecast or a warning tied to a specific time frame. Is the plate tearing apart a sign the fault is under more stress than before? Not directly, and not in a way that's been confirmed. The tear itself is happening on a structure separate from the main locked megathrust that generates Cascadia's biggest earthquakes. Researchers are investigating whether this segmentation indirectly affects how future ruptures propagate, but that work is ongoing and no firm conclusion has been reached. Did this just start happening, or has it been going on for a while? The tearing almost certainly reflects a process that has been unfolding gradually, likely over a long stretch of geologic time, potentially many thousands to millions of years. What's new isn't the tearing itself. It's that scientists now have clear enough imaging to actually see it and describe it in detail. This is a discovery about improved observation, not a sudden new event. That isn't Simsu. Should people along the coast do anything differently because of this? No. Standard earthquake and tsunami preparedness for the Pacific Northwest, knowing evacuation routes, keeping an emergency kit, understanding regional risk, remains exactly as relevant as it was before this study. and this research doesn't add any new specific action item beyond that existing guidance. Well, why does this discovery matter then, if it doesn't change the immediate risk picture? Because earthquake forecasting is a long-term science, built up over decades by incorporating exactly this kind of structural detail. A clearer picture of how the incoming plate is built, including where it's already fractured, gives researchers better raw material to eventually refine the models that predict how future ruptures might behave. It's a foundational improvement to the science, even though it doesn't translate into an immediate change in personal risk today. For first, the bigger picture. Subduction zones are, in a sense, planetary machinery. Over tens of millions of years, they've built mountain ranges, fed volcanic arcs, and slowly recycled old ocean floor back down into the Earth's mantle. For just as long, scientists have understood not that these systems eventually end, but not in any directly observed sense exactly how. For the first time, researchers now have a real physical answer to at least part of that question. It doesn't end with a single dramatic break. It ends the way this discovery describes it, unevenly, in fragments, with some sections still working while others have already fallen still. A slow structural unraveling, hundreds of feet beneath the Pacific, that took a specially outfitted research ship, years of data processing, and a fair amount of scientific patience to finally see clearly. It's a genuinely rare thing in geology, watching the ending of a process that normally takes millions of years to notice, unfolding in evidence gathered within a single human lifetime. That, more than any single number in this story, is probably the most remarkable part of it. Most of what we know about how planets work comes from studying processes long after they've finished, reading the outcome in rock that's already cold, already settled, already still. Catching one of these systems mid-collapse with instruments precise enough to actually resolve the structure while it's still forming doesn't happen often. It's the kind of opportunity that reshapes a field, not because it overturns everything researchers thought they knew, but because it finally lets them check their oldest assumptions against something real. The Juan de Fuca Plate will keep tearing long after this particular study fades from headlines, at a pace far too slow for anyone to feel or notice directly. What's changed is that, for the first time, scientists have a genuinely clear window into watching it happen. And that window is enough to rewrite part of a very old, very quiet story that's been unfolding beneath the Pacific for far longer than any coastline above it has existed.